Hey guys, in today's lab, what you're going to do is you are going to measure the speed of light using a microwave. So light comes in a lot of colors. You have blue and purple and green and orange, and those are only the colors you could see. There are a lot of colors you can't see. Ultraviolet, X-rays, radio waves, infrared light. Those are literally just colors of light that your eyes, due to our biology, are not able to detect. So, what is light? Light is an oscillating electric and magnetic field. So that statement has a lot of things in it. Let's unpack what we mean. So let's assume that I wanted to draw an electric field in a region of space. So I could draw an X and Y axis to represent position, and then I will draw my electric field. Let's draw the electric field something like this. So we have something that's curling up and to the left, and maybe the electric field is going to do something like that, and then there. So here's an electric field I drew. Now, let's think about what I really drew in this picture. Ultimately, everything on the whiteboard here is just a bunch of arrows, but what do these arrows actually mean? When I draw an electric field in this form, what I'm trying to do is I'm trying to artistically represent a quantity that has a magnitude and a direction. So, the electric field exists everywhere on the board, but some arrows I drew bigger than others. The arrows here do not correspond to length. The arrows here correspond to strength. So the locations where the arrows are drawn very long, that represents an electric field that is really strong, has a really large magnitude. The areas where the electric field arrows are really short, well, that's just where the electric field has a very small magnitude. So, the electric field does exist everywhere. The length of the arrows that I drew of the electric field, they don't have anything to do with distance. They represent strength. So, a light wave is an electromagnetic wave, an oscillating electric and magnetic field. Now, you have an electric field that oscillates. When something oscillates, it is pointing up, then pointing down, then pointing up and pointing down. And it's not just pointing down and then up and down and then up. What happens is it goes from zero, down small, down medium, down large, down medium, down small, zero, up small, up medium, up large, pointing up medium, pointing up a little bit, then a value of zero. So here is a picture of an electromagnetic wave. What we have is we have an electric field that is oscillating in the y direction. So the electric field at the origin was drawn to be zero. And then the electric field is pointing up, pointing in the y direction, but it's not that strong. Then the electric field is pointing in the y direction and is really strong. Then the electric field is pointing in the y direction again, but is not that strong. Then the electric field has a value of zero, a magnitude of zero. And then the electric field is pointing downward. So in this picture, the electric field only exists along the x-axis, but the electric field is pointing in the y direction or in the negative y direction. Now, similarly, the magnetic field only exists along the x-axis, but the magnetic field is sometimes pointing in the z direction out of the board, and the magnetic field is sometimes pointing in the z direction into the board, and then pointing out of the board again and pointing into the board again. And sometimes the magnetic field is pointing out of the board and is really, really strong. Sometimes the magnetic field is pointing out of the board and is really, really weak. Over here, the magnetic field is pointing out of the board, just like it is over here, but the strength of the magnetic field is not that large. So you have an electric field that is pointing in the y direction, and oscillating between 0, really large, back to 0, then it points in the negative y direction, back and forth. And you have a magnetic field that oscillates in the z direction. And these oscillating electric and magnetic fields are moving in the positive x direction. So light is an oscillating electric field, an oscillating magnetic field that moves. And the direction of E, the direction of B, and the direction of motion are all perpendicular to each other. Now, how are we going to use a microwave to actually measure the speed of light? So microwaves are a type of light that was named after the kitchen appliance when the microwave was discovered. So microwaves are a light that has a wavelength of around a few centimeters. So as you read in the lab and in the section in the textbook, wavelength is one way of representing light, and wavelength is the distance from one peak of a wave to the next peak of the wave. Or wavelength could be similarly thought of as being the distance trough to trough. So wavelength is a distance that is given by the symbol Greek letter lambda, and wavelength is something that you would measure in meters, or kilometers, or nanometers, depending on what type of wave you're working with. So a microwave is a color of light that you are not able to detect with your eyes. The wavelength of microwaves is around a few centimeters. So now let's say we have a cavity. So here's a cavity that I could think of as being my microwave oven. And we want microwaves to exist in this cavity. So we want microwave light to exist in this cavity. We don't want microwave light to exist outside the cavity. Now, if light does not exist somewhere, that's like saying the electric field is 0. So outside of this cavity, I want the electric field to be 0. Inside the cavity, how could the electric field behave? So there are several possibilities. Now, I want the electric field to be continuous and smooth everywhere. So in calculus, you would say you want the function to be continuous and differentiable. Continuous just means you have a value everywhere. Differentiable means you don't make any sudden jumps. If you could define a derivative at every location, that means you have a value at one location, and at every adjacent location immediately next to it, the function changes smoothly. There's no cutoffs or cliffs or singularities where it blows up to infinity, nothing like that. So if I am to have some microwaves inside this cavity, I want the electric field inside the cavity to match the electric field outside the cavity. So if I'm barely on the inside or barely on the outside, I need those two values of the electric field to match, because I don't want the electric field to make a sudden jump anywhere. So let's think of what could be the behavior of an electric field that satisfies this requirement, where the electric field could be anything at all, but it must be 0 on the boundaries of the cavity. Well, one possibility is the electric field could just be 0 everywhere inside the cavity. But if the electric field is 0 everywhere, that would not be a very interesting result, because that's like saying if the electric field is 0 everywhere, we have no light. Now, in this discussion, I'm only talking about the electric field, but everything I say about E would just as well apply to magnetic field, and it will follow the exact same rules. But this is not the only possibility for the electric field inside a cavity. Another possibility for the electric field is you could have something like this. If I have a single wavelength inside the cavity, well, I am satisfying the requirement that the electric field is 0 on the boundaries. So a wave inside my cavity like this is allowed. There is another possibility. Instead of having a wave inside the cavity like this, I could have two waves inside the cavity. So I could have a wave that looks like this. Here I have two wavelengths inside my cavity. Or I could potentially have three wavelengths inside this cavity. I'm never violating the rule that the electric field must be zero. That I am never violating the rule that I want the electric field to be zero on the boundary. Another possibility is I could have half of a wavelength inside this region. Half of a wavelength inside this region, I'm still satisfying the requirement that E is zero on the boundaries. What I'm not allowed to have is I can't have something like this where I have zero on one boundary and then non-zero on the other. I have to have the electric field be zero on the boundaries. So microwaves are of the order a few centimeters long. The microwave oven in your kitchen might be 20 or 30 centimeters across. So you'll have about 3 or 4 full wavelengths of microwaves inside your cavity. So, okay, we talked about how we could have a wave just existing inside a finite volume region. In the next video for this lab, I am going to talk about how microwaves heat food and give you a little bit of what you're doing in this lab, and then you'll be good to go and fill out the sheet.